Okay, YouTube, in this video we're going to be exploring what we refer to as summation notation, and of course the root here would be sum. So we're going to be looking at a convenient notation, so just a way of writing something, for the sum of the terms of a finite sequence. So recall that a sequence is just a list of numbers such that it has like a first term, a second term, so on and so forth. We could make up our own sequence here, but like 3, 5, 7, 9, say 11. This is my finite sequence here that has 5 terms. But let's say that I want to find the sum of all of these terms right here. There is a convenient way to write this long sum right here, which isn't that long in the first place. But the way we do it is using what we refer to as sigma notation. So this is the capital Greek letter sigma, this capital E looking thing here. And what it stands for is the sum of a bunch of the terms of a sequence. So you can clearly see that we're adding the terms of a sequence. So we're adding, and in this case, we're going to write the first n terms of a sequence. And so when we are adding together the first however many terms of a sequence, where we stop at the nth term here, we can write it thusly. So we're going to define a few things with this sigma notation. Starting with this, I is called the index of summation. So what you see down here is the I, and we refer to this as the index of summation. We say n, I'll go ahead and write this here, the index of summation. N we refer to as the upper limit on our summation. And what we're going to do is we're going to kind of label these here. I would say that the index down here, I, equaling 1, that's our lower limit. We're going to label this also lower limit. So in every possible case, what we're basically saying is that in our sigma notation, what we're going to do, I guess I'll label this also as our rule. We are going to take the rule for this particular sequence, the rule. And we are going to start at the whatever term here. We're going to say starting term number. And this number up here is going to be our stopping term number. Stopping term number. So essentially what this says is, for some rule a sub I, where I is our index, what we're going to do is we're going to add up, starting at the first term all the way to the nth term, all of those terms of the sequence. So you can see that this really says add up all the terms of this rule starting at the first term and stopping at the nth term. Okay. So when we look at summation notation, like these two examples here, let's go ahead and really read these for what they say. This right here, we're going to label a few things. This is our rule. As a matter of fact, I can write this over here. We say a sub n is equal to 3n. If I'm writing it with an n, I suppose we could call this a index I. 3i, these two rules would mean the same thing, just with a different letter. But we're saying that our index is I, and we're starting at our first term and ending at our fifth term. So we'd say this was our starting term, and this is our end term. So what this really means to do is to go find this, a1 plus a2 plus a3 plus a4 plus a5. But in this case, we actually know our rule here, ai, which is equal to 3 times I. So really what we're going to get is this. We're going to get 3 times 1 plus 3 times 2 plus 3 times 3. Sorry about the mutant 3 there. Plus 3 times 4 plus 3 times 5. Where in every instance, we just found the term value for each of these first 5 terms. So we'd say this is 3 plus 6 plus 9 plus 12 plus 15. And in this particular instance, I suppose we get 9 plus another 9 here would be 18. 18 plus 12, I suppose that'd be a 30, and 30 plus 15 here would give you a 45. So the value of this sum really is 45, but what it really said was add up the terms of this sequence right here, starting at the first term and ending at the fifth term. One thing I do want to say about sums is that you don't always have to start at the first term. So taking a look at this next example here, I'm going to write this here. I'm going to write this as a k. I'm going to use k as our subscript because that's our input variable and our index on our sum here. But what this really says is take this rule and go add up the third term through the sixth term. So again, what we're finding here is this. We're finding a3 plus a4 plus a5 plus a6. All we are doing really is finding the sum of the third through the sixth terms. So we're going to plug these in here. We say, what is a3 equal to? So we say a3 is equal to 1 plus 3 squared So we would get 1 plus 9, which is 10. We say A4. What is A4 equal to? 1 plus 4 squared, which is equal to 17. So we get plus 17. Plus now A5. A5, the fifth term in this sequence, would be 1 plus 5 squared, which is 1 plus 25, so 26. So 26, and then finally A6. We say A6 would be 1 plus 6 squared, which would be 37. 1 plus 36 is 37. So we're going to sum all of these terms up here. I suppose here we get a 27. Now 27 plus 26, that would have to be a 53. And 53 plus 37 is 80, 90. So we get 90. So 90 is the value of this sum right here, but 90 is also the value you get when you add up the third through the sixth term of this particular sequence defined by this rule. So before we piece out of this video, I want to talk a little bit about the properties of sums, starting with this first one here, where we say C is a constant. If you ever take the sum, and this has to be starting at the first term, so this is first term if this property is going to work. On all of these, it has to be the first term, but if you're going from the first term through the nth term of a rule where the rule is just a constant, this would be something like this. Let's put an example. If I said I equals 1 through 5 of 3, what this really means though, since this is your rule, right, this is our rule, it means that our first term here, A1, is actually just 3. It's always 3 here, actually. So we get our second term is 3, our third term is 3, our fourth term is 3, and our fifth term is 3. So what this rule says is you always get C times N, where N is our upper limit of summation, or our upper bound, okay? So in other words, what we're saying is we acknowledge that because the rule is always 3, then really we have 5 terms that all have a value of 3. We're just going to multiply the constant that we have here times the upper limit on summation. So we'd say 15, but really 15 because we get equal to really 3 times 5. So we get 15. So now our second property here says that if you have now the sum starting at the first term and ending at the last term, which is the nth term, of a constant times a rule, so we have a rule here, A sub I, you can actually take that constant and put it out front of the sum and apply it last. So for instance, if I had something like 2I, and I take the sum of this, we'll take the sum of this starting at the first term and going up to, suppose the nth term here, we'll call it say 10. This is just an example. This would be the same thing as 2, where we pull that constant out in front, where we could just take the sum of I from going from I going from 1 to 10. We could do this part first and then just double our answer there, okay? And then these last two properties basically say this here. And this first one's going to sound confusing, but we say the sum of the sum is the sum of the sums. In other words, if you take the sum, which is this sigma here, of a sum, which is this AI plus BI, which these are just two rules added together, then that would be the same thing as just the sum of the A part plus the sum of the B part in terms of those two separate rules. It'll make a little bit more sense when we read it this way, but we say the sum of the difference is the difference of the sums. Difference is the difference of the sums. In other words, if we take the sum of this difference of rules right here, that's the difference of the sums of the two rules individually. Cheers.